So then we can start with the webinar. Again, a warm welcome from my side to this webinar of the Open Innovation Service of the InShaPe project. Together with me from the InShaPe consortium in this call are Mikkel Pettersen. Maybe Mikkel, you would like to introduce yourself really shortly.
Yeah, I can do. I'm Mikkel Pettersen from Earlycon AM, leading a R&D department, and for InShaPe project, I'm the exploitation manager.
Okay, then Markus is another colleague from the consortium from EOS. So Markus, a short introduction.
Yes, so my name is Markus Birk. I'm from EOS. I'm a system developer and I'm managing the InShaPe project from the EOS side.
Okay, so we will answer your questions after this short webinar. And first of all, the outline of the webinar is that I will give you some general information what is InShaPe about. We will explain to you our KPIs. We will explain to you really shortly what we are doing so that you get the complete picture. And then we will move on to our already existing use cases, which will be explained by Mikkel Pettersen. And then we will talk about the Open Innovation Service also by Mikkel Pettersen. And at the end, you have the possibilities to ask questions about the call, about the project, what we are aiming for, and so on. So I will start with a short introduction on the InShaPe project and explain to you the vision and the mission. So what we would like to do in InShaPe is to make metal-based additive manufacturing faster, cheaper, and more sustainable. We are mainly focusing on the powder bed fusion process with metals, and the project is underpinned by two technical innovations. The first one is the beam shaping unit and the light engine, where we will talk about later, and the second part is multispectral imaging to get a better understanding on absolute temperature development during the powder bed fusion process by using different beam shapes. So far, we are 10 project partners. I will name the 11 partners on the next slide. The project duration is 36 months. We started 1.5 years ago, almost exactly 1.5 years ago in 2022, and the budget of the project are 7.2 million. Here we see our actual consortium. The consortium is led by the Technical University of Munich, so I'm the coordinator of the project. Then we have different partners from Germany. EOS, for example, is one main partner who has developed, for example, the beam shaping technology. Then Earlycon. As scientific partners, we have TU Eindhoven, who is dealing with the topic of artificial intelligence mainly, and another academic partner is Technion, and we have different use case partners like BMED, Aenium, and Nemexi. We will talk about the use cases later, and one new partner via an hop-on call, which is the IMT in Slovenia. Here you see a picture on where we were spread over Europe and Israel. So the motivation is that laser-based powder bed fusion is so far an established industrial manufacturing process with a great potential. We see this on this part, which is a part of one of our partners, Aenium, a combination of a copper alloy with Inconel, for example, but we have still some challenges. And the challenges we are addressing in the project is that we would like to increase the productivity by a factor of 7. So this is the one limitation in the state of the art. We would like to reduce the part costs around 50% to make it also attractive, the additive manufacturing process in general, for other industries and new applications, for example. And we hope that you can bring in a new application. We would like to reduce the energy consumption by 60% and the scrap material, like scrap due to support structures, but also scrap material due to spatter formation and so on by a factor of 30%. So if you have a look on the standard process, the key aspect in powder bed fusion is the light engine. And in terms of light engine, we have changed this one, or EOS has changed this one with a beam shaping module, which I will explain to you later. If you have a look on the state-of-the-art process where you use a Gaussian beam profile, you see, or you have definitely, if you're working in the industry, seen this picture before, that we have a highly dynamic process with a lot of spatter formation. And this is the reason why we are using these two technical innovations in InShape. And the first one is an AI-based beam shaping module where we can adjust the energy input in terms of space to any structure we would like to create. So any beam shape we would like to create, we can create at the end. So we have a programmable beam shaping unit to tailor the beam shape based on our target values we would like to reach. Some of our partners, and this is explained by Mikkel later on, are aiming for productivity, but also some of our partners are aiming to tailor the microstructure, for example, or to reduce the surface roughness on downskin surfaces and so on. And therefore, at the moment, we are evaluating what is the perfect beam shape for our KPIs or target value. And at the end, our idea is to have a recipe book of different beam shapes for different features, for example, for different materials, which can be used in the different application fields we already have, and hopefully in one additional field you bring in with the open innovation. If you change the energy input in space, you need to measure what is the result during processing, and therefore we are using multispectral imaging to evaluate the absolute temperatures during processing. This is something we will not focus on today. We are quite far there. We can measure temperatures, and now we are going on in this direction to a control system during processing. But the focus of today should be the beam shaping module and the possibilities there. Here you can see some possible beam shapes we have already created, like a ring-shaped beam profile, a top-height beam profile, some kind of C shape. We also created a shape which looks like a chair to get a really homogeneous temperature distribution and so on. The question again arises, what is the target value? In our case, I explained it, and Mikkel will explain this, that we are focusing on different topics like productivity or tailoring of microstructure. One example for the process where the aim was to get less dynamic processing, a smoother melt pool and a bigger melt pool for productivity is a video you can see here. Therefore, we use the C shape, and what you can see is that the process is less dynamic, we have less spatter formation, and also the productivity is increased since the beam profile is bigger than the standard 80 micrometer Gaussian beam profile, for example. So this is something which we have already achieved. So on that slide, you see again the different technical innovations we are working on. Today, we are mainly talking about this next generation light engine, the KPIs we are aiming for, and the process control topic. So this was the idea and the technical innovation behind the project. Now we are moving on to what use cases we are already involved in the InShape project, and therefore I hand over to Mikkel.
Thank you, Katrin. And exactly as you said, the motivation for showing you also what we have in the project already is to give some ideas of where we can employ beam shaping to improve our products. And I'll go through the 4 use cases that the existing partners already submitted. So the first one is the one on the left from Aenium, which is a combustion chamber for a small rocket system. Of course, here we're talking about a copper alloy. So productivity, printing copper alloys with existing standard infrared laser systems is a key topic. So really increasing the print speed itself using this technology. As it has, as we can see, internal channels for fluid flow, surface roughness is a key element. So achieving a very smooth, nice surface in the printed state is a huge benefit. And last but not least, the microstructure control. By printing this alloy, they can get to a very specific microstructure state that really balances between the conductivity that is needed to survive the heat and the strength that has to be in the part as well, doing this very intense hot fire process that is for a combustion chamber. And this is something that could be achieved only through AM. But today, the sacrifice there is productivity. Then we have the Oerlikon case, the one we submitted. Here, the material is an Inconel 718 impeller. Of course, we want to achieve productivity. One part of that is through the printing process, so being able to deposit the material faster. But another aspect of this is reducing the amount of not the traditional support structure, but structural support. On this part, we add a lot of material to keep the shape. Basically, we print a ring around it of solid material to maintain the shape due to residual stresses. So by managing the stresses and printing faster, we can really improve the productivity of this. Of course, as a pump system, we have internal surfaces that otherwise needs polishing. So the better we can print these surfaces, the better it is, the less we have the post-process. And of course, the, let's say, traditional support structure is a topic to avoid inside these channels because it's a challenge to get out. And of course, also a point where we print material that is essentially wasted, so creating scrap from this process as well. If we go to the next slide. So here we have the last two. So on the left, we have the cylinder head for a chainsaw from Amexi. Here we have aluminium, again, a material that we could improve the absorption of the laser power into to help print faster and productivity. But another real key goal of increasing productivity of this one, which is potentially a high volume part, is to stack the parts in the Z direction. So really fill up the build chamber with a whole bunch of these cylinder heads. To do this, again, we have to manage the residual stresses to avoid that they distort. And of course, minimize the amount of support shock that's needed because we cannot connect every single part to either the part below or even the base plate because the amount of post-processing we would end up with would be enormous. So again, similar points of how do we improve the print productivity? There's an element in the process itself and an element in what material we have to print around it. And the last example is the gas turbine part that we have from BMIT, where the material again is Inconel 718. Productivity in the process is a topic, but here we're talking about gas turbine parts that runs tens of thousands of hours. So really the core is, yes, we want to print faster, but it cannot be a sacrifice of the quality of the part. We have to ensure we have good microstructure, consistent microstructure every time the same over and over again in a mass production state. And again, with the internal surfaces, the veins we see there, low surface roughness is a key element to achieve in the printed state of this component. So there's some elements that goes again across these, and then there's some that are new. And we want to show you this demonstrator, which is one that our colleague Marcus from EOS printed recently to show how far we've come in the development already. So here we have this complicated part from a student team that's part of the Hyperloop challenge. And what we see is we have a part that's printed with multiple beam shapes, multiple parameter sets, and multiple layer thickness, all within one build. The pictures of the part does not do the part justice. It looks really, really good in terms of the surface roughness, in the terms of the details of the part in the printed state. And if we look at the KPIs, and these KPIs are mainly around the print process, we already achieved almost a 5-time productivity of this part. It costed almost at the 50% target that we aimed for. Energy consumption significantly reduced, and of course more waste reduction. So really, this shows that there's a lot of potential in, let's say, an early application of this, not where we have done all the complicated work that Catherine also mentioned with the AI to determine the optimal shape for different parts and processes. So this is perhaps a more simple application of the beam shaping, although complicated with multiple layer thicknesses and parameters and shapes on a single part. So why should you join us? So this is hopefully you've achieved got some ideas from what we've shown. So why this could be of interest to your product. And really, we're talking about the newest inventions within AM. If you attended Formnext, you will have heard several of the machine OEMs talking about beam shaping being one of the next things they're rolling out on the system. So hopefully in not too long future, that's standard for the process and something you would be able to take advantage of for your products. We are very interested in exploring additional applications at different challenges from other users, in addition to the 4 that's in the project, to see where's the limits, where's the challenges for this new technology. Sorry, we're short fire alarm here. We have the competition aspect. Hopefully this stops. There's a competition aspect of this, so we cannot do every single application that will be sent to us. So we will select the best ones, the ones that pushes the technology further or opens up new areas that we have not included in the current 4 use cases. And of course, we want to see this opportunity to reduce the CO2 footprint, and for a lot showing that as a roadmap for how your products over time will be able to have a less CO2 footprint is something that could be of interest. And you will get to show that through this process. If you come with us, there's a route to do this. If you do the next slide. So on the material, we're pretty open material. However, we prefer if it's materials that are similar to the ones that we've used in our 4 use cases. This makes it a lot easier, and we might ask you if it's okay to substitute the material in a class close to what we have. We've having a pretty broad spectrum with both Inconel, copper, and aluminium alloys, but for sure we don't cover all the alloys. The dimension is an EOS M290. So a standard machine as we know it. That is the maximum size we can print. We need some raw data. We need some CAD files to work with, and for sure it has to be something that we can do some publication around. It doesn't mean we have to show every data, everything that you bring to us, but a key element of this, because of the EU funding, we have to make some dissemination and communication around what we do. So elements of what we do together has to be available for publication, but not everything that of course is shared with us have to be made public. And so last but not least, some information about how to apply. So we need some information about you and the team members, and of course the more we can have around the product, the better, to make the assessment of which products we want to or we will choose for this competition. Some KPIs of what you would like to think. So maybe based on what we discussed today or presented today, what could be the key things that would be important for you to achieve with your application. And of course, we have the how to apply by sending the information to this email listed here. That's also what you can see on the web page with the link that's down below, and probably where you found the registration for this webinar as well. So that's the overall description of what we are offering in our open innovation service, and we really hope that we find some interesting components to add to the use cases in this project.
Yeah, so this was first introduction from our side. Now it's time for you, if you have some questions on the open innovation service, like you already have a part in mind or a material and so on. Are there any questions? If there are any questions, I would ask the participants to maybe raise their hand, and then we can answer these questions. Okay, there's one question from Sören. Can just open the mic and ask the question.
Hello, thank you very much, first of all, for the informative presentation. So I'm working on water electrolysis for the generation of or production of green hydrogen, and additive manufacturing for some parts would be a very interesting manufacturing process. The issue is, however, for an application like that, we would need to build a part out of titanium or some titanium alloy. Would that be already a factor where you would say, okay, this is not really applicable for this project, titanium, or shall we still give it a try?
So maybe I think it's not a limitation. So we said the main thing is it should be out of metal. What would be important for us is that it's really a challenging part. Like if it's a standard state-of-the-art part and you can easily print it and it's not that challenging to use. Beam shaping, for example, maybe it's not that interesting. The background why we prefer materials we already knew is that we have a parameter developed for these materials. If we would like to now start with a new material, we have to think about parameters. But for a first showcase, for example, another material could also work. So I would recommend to hand it in, and then we can have a look on the part, how it looks like, if we think it's really challenging, if you have specific I can imagine that you have specific requirements for the surface roughness and so on, and then we can evaluate this. So.
Okay, yeah, thank you very much. And then also a follow-up question. Do you already know how many applications will be selected for manufacturing?
So at the end, we will select one application, for us, most promising one, most challenging one, most interesting one. We have, we will also have a look on the applications we already have, but it's not excluded if someone would like to apply with an impeller that we do not choose this impeller. It really depends on the application. But for example, what you are talking about is a completely other application area, which is definitely in our scope and interesting.
Okay, yeah, thank you very much.
You're welcome. So, do we have further questions?
So I lost connection for a second, and in the middle of the material discussion, I hope we said it. But the good thing, if you're looking for something like a Ti64, it's an unknown material within printing. So again, it helps a little bit on the novelty. If we had a completely new material that's not been printed before, that would be a bigger step for us compared to this. I don't know if that was what you already answered, Catherine. If it was,
yeah. I said it's important that it's metal, and titanium is titanium 64 is a well-known material, but nevertheless we have to develop. We do not have on hand the beam shaping parameters for this material, so this is the challenging part. I think there was an additional question from Francesco, but is there an additional question? Yeah.
Hi.
Hi.
Good evening. I have just a question. Do you have a list of requirements, both mechanical or thermal, for the component to manufacture?
So actually the requirements for the component in terms of thermal behavior, mechanical behavior, I think this depends on the use case and comes from the use case. For us, the main thing is that it should be printable. I think that's I'm not sure if the part you're thinking about is something you at the moment print with a standard process and now would like to use the beam shaping process, or if it's something which is not printed so far. What we are doing is we will have a look on the part and evaluate whether we can print it in terms of size, material, and so on. And then for us, we will see what, for example, your goals in terms of mechanics, thermal behavior, and so on are. I'm not sure if Miko, you would like to add something, or
okay, no, I understood. If I understood correctly, in the use case, I should provide also information about the mechanical, for example, mechanical or thermal requirements to be satisfied during the process in order to benchmark it with a standard SLM process. Is it right?
Yes. So what we do, if your part is not printed so far, we will evaluate what the KPIs would be if we would print it with a standard process and then compare it also with our beam shaping process. This is something we can also offer.
Okay, thank you.
You're welcome.
You can look a little bit like it with the Beam It use case. where the goal is microstructure control, and some of that is to reduce variability. So we're not making a fundamentally new microstructure of the Inconel 718. A lot looks like what you would expect from a printed microstructure, I have to say. But we have a much more uniform microstructure, which helps on qualification and also on the that the part is performing the same every time and the performance is expected the same. So that element, but we're not fundamentally changing how a 718 printed works.
In your project, using this methodology, are you modifying the production rate by modifying the density in specific areas of the part of the component, or
no? So what we are doing is actually the aim is to get 100% dense parts. What we are doing is we are changing the melt pool size. So we are creating a bigger melt pool, and this means that we can also change the hatch and so on, and therefore we are increasing productivity. I'm not sure if you see the slides, but here you see it nicely. This actually part was printed with a parameter set of 40 micrometers, but a state-of-the-art parameter set. So this would be the parameter you use in the state-of-the-art, or if you change it to a 80 micron layer thickness, you would reach in the same time, like we have created this part with beam shaping, only for the 40 microns this amount of the part, for the 80 microns this amount of the part, and for the with our beam shaping technology, we can print the complete part, since we have a larger melt pool and so on. But the density is again 100% when you are aiming for 100% density.
Okay, I understand. So you are modifying the parameter set of your of the beam in order to, and optimizing, of course, the this set of parameters in order to creating big slices without decreasing the coherent microstructures of your of the SLM component. Okay, I understand.
This would be the idea, yeah.
So we're sort of breaking the rules, right? By introducing a new technology, we are not limited by the normal that if I speed up my process today, I would sacrifice my quality. I will get some more porosity. This would be the normal way we would have to improve the productivity with state-of-the-art what we buy in machines today. But by introducing the beam shaping, we break those rules, and it gives us another room to play where we can have a larger beam or a different way to add or interact with the powder, which means we can actually print faster, but we don't get this sacrifice of quality.
Okay, perfect.
Welcome.
And about the file format, I noted that there is no STL or OBJ file. So do you expect a conventional manufactured component to print with with an SLM technology, or can I send you also an STL file for a more organic shape?
I think this maybe can be answered by Marcus, because EOS will print the part.
Yes. So
is the CAD file a mechanical shape, or can be also a mechanical shape?
It can be also an STL file.
Okay, thank you.
You're welcome. Do we have additional questions? Okay. If there are no questions anymore, we thank you for your participation. And we will upload also this webinar to our webpage that also all of the other applicants can get access. So thanks for participating and have a nice day.